So I will be explaining my solution to the 2025 Putnam Problem B1. And surprisingly, I was able to get full credit on this problem. And this was a very accessible problem because it didn't require you to know any advanced math. It was really just pure problem solving. So like if you're taking like the Putnam or just like any contest that seems intimidating and you don't really think that you're like that good at math, do not be intimidated because this problem was it wasn't as deep as you might think it was. And so yeah, I was able to receive full credit, and I didn't study for the Putnam, so it's not as if that's why I'm saying like this problem was just genuinely pure problem solving. You didn't have to study any Putnam math or whatever. As long as you asked yourself the right questions and you understood the problem on high level, then it was a very accessible problem. And so the problem goes: suppose that you have these points on a plane and they have this following condition though, right? These points are colored two colors, red or green. For the sake of my solution, I'll use blue and red because those are the only colors available on Zipboard. But the important condition is that every three non-collinear points, so every 3 points that do not form a line, um, if they are all the same color, so if these three non-collinear points are all the same color, then the center of the circle that's formed by these non-collinear points must also be that color. So suppose we have red here, a point here, a point here, and a point here. Then the center of the circle might look something like this. It's pretty bad, but we just have these points that you can see. Then you understand that this center must also be red. And so the idea is that if you have this constraint, um, then the idea is that the entire plane should be only one color. You want to prove that all the points are the same color. So if you think about this problem at a high level, it feels very intuitive. That like all the points are the same color. Like if you like, there are a lot of like if you think about it, like in the plane, there are like infinitely many like triplets of like non-collinear points, and then that also forces another point to be their color as well. And so it seems like you can just shade the entire plane like red. Like this result does feel intuitive, at least if you just think about it, like it kind of makes sense. There's like infinitely many triplets of like non-collinear points, and like that triplet forces some other point to also be red. And then you can also like kind of use the same idea. You maybe use this point, look for another triplet, force another point to be red. It seems like you can sort of like just color every single point to be red. And so this seems like kind of intuitive. But the so but it's like, obviously this idea of like sort of coloring infinitely many points of red, it's like it's sort of hard to just inductively show that like every single point must be this color. Like that's a like it's not that it's a wrong way to think about the problem. It's just not necessarily it's hard to like describe. It's hard to formalize, but it's very intuitive that you can sort of just inductively just like sort of like if these three colors are colored red, then that implies that this is red, and so like you can sort of just like maybe inductively fill out like the entire plane, but like these are not even integer points. It's just like the entire plane is red. So like this doesn't seem like a good strategy, at least to me on the contest. But a better strategy is using proof by contradiction, right? So we're going to assume that, okay, suppose for the sake of contradiction, there are 2 points that are colored different, okay? Then we're going to show that it leads to some contradiction. So the idea is we're going to start with the idea that there is a red point in this plane. Yeah, maybe let's make this more visible. But there's like this red point in this plane, and there's a different color. There's a blue point in this plane. So this is for the sake of contradiction. Assume that maybe this is point P, and this is point Q. Assume for the sake of contradiction, the plane has 2 points that are different colors. Somehow this is supposed to contradict something in the problem. And this is where you should be thinking, what exactly should this contradict, right? Well, it should contradict this very condition that for every three non-collinear points of the same color, there's a center, their center for the circle, right, that's determined by those points, their center must also be in the color. So the idea here is that if we're going to do some proof by contradiction approach, and we're starting with this initial configuration of two different color points, we somehow must contradict the idea that if we have a circle of three of this of we have a circle, right, where where the 3 points are all the same color, right? So for example, let's say we have some red circle, right, where like the red circle is just like, there's 3 points on the perimeter that have the same color. The contradiction should be like somehow we get like a blue center. Somehow we get a blue center. Then we contradict the condition, right, of this problem. Right? The way that you contradict this condition is you form a circle, some blue circle with a red center, or a red circle with a blue center. And I'm just gonna use like those different colors instead of red and green. So that's the idea. So this is sort of getting an understanding of like maybe some sort of approach that you should, some method of attack that you should have. And the problem is that like if I'm going to do some proof by contradiction, right, I'm going to try to contradict something in the problem, it probably is this condition. Like somehow the intuition is that starting with two different colors, right, is supposed to contradict this condition, right? And so the idea is that somehow starting with, P and Q like this is supposed to create some circle, some red or blue circle that has a different center than the perimeter, right? And so that's like the intuition of the problem. That was my thought process. And so I was thinking about like, what can we do? We have these 2 points. What should we do? Well, we're trying to form circles, right? We're like our idea is that we're trying to form like a circle that has a different center, different color center, like some red color circle that has like a blue center or vice versa, right? So we should start drawing circles. That was like, why would you not? Like, okay. So the first circle that seems like that was intuitive for me to draw was I'm just going to connect these. I'm just going to connect the segment, right? So suppose I connect, you know, the segment here, and now I'm going to draw a circle with radius PQ. So it's centered at Q, and it has radius PQ. Okay, maybe I just make this a little bit smaller. Okay, so here's a circle with radius PQ. Now the idea is that I drew a circle because think about it. If I'm trying to draw circles in this problem, then so there's gonna be like this circle needs a center. There's only 2 points. So the first circle I'm gonna draw is maybe centered at Q, and maybe its radius is just P. It's PQ. That seems like the most logical circle to draw in the beginning, right? So I'm trying to like motivate like what I'm trying to do is like in my thought process, I was just like, I'm trying to draw a circle because ultimately I want some circle that violates this condition. So I'm going to draw a circle centered at Q. Now I draw a circle centered at Q. Let me draw a circle that's now centered at P, right? Because think about it. The idea here is like in this case, you just have a circle, but it seems like one circle is like doesn't really tell you that much. In this case, um, because this circle here only has one red point, right? It needs three red points for it to be declared a red circle, right? If something is declared a red circle, that basically just means that like um it has three red points on its circumference, and so it needs a red center. This circle we have right now only has one red point on its circumference, so it is not sufficient. So the idea here is that we might need to draw like another circle to somehow create like so we can declare it as red or blue, right? That's what we want. So the motivation is maybe we draw another circle. What center should it be at? Well, maybe we draw a circle at centered at Q. Let's draw a circle centered at P. So that's exactly what we're going to do. We're going to draw a circle centered at P, and it's going to take the radius PQ. So we draw the circle, and this has radius PQ. Now here's very very interesting. Here's a very interesting thing, is what should the colors of these intersection points be, right? So I'm going to look at these intersection points here, right? Right. What should the colors of these intersection points be? So I'm actually gonna box them out just so we have an intersection point here. We have an intersection point here. What exactly are the colors of these intersection points? So suppose, I mean, without loss of generality, right? I'm gonna just suppose that this is a red point. This is a red circle, right? I'm just because, for example, I have no idea what the color of that circle should be, and in the problem, we know that for every non-collinear points, like the center of the circle must also be the same color. Well, this intersection point is not serving as a center of any circle with points around it, so it doesn't feel like it has any it's not constrained to be a specific color. So without loss of generality, I'm just going to assume that it's like of color. I'm gonna first gonna call this. Let's call the point here A. Let's call this point here B. I'm gonna color this like uh red. So I color this red, right? Now, here's the idea. Because we have this constraint that, like, we think of B, right? Can B be red? The idea is that it cannot be red, because if this point is red, then if this and this point is red, then we violate the condition, right? We have a red circle, right? These A, P, B, that has a different color center, and that violates the constraint. So it must be like, by construct, like we are forced because we are forced to assume that this is blue. We're basically forced to assume that the intersection points have different colors. That's basically the assumption. If you assume that they have same colors, like for example, let's assume that A is blue, then we're gonna create another. We're gonna contradict the condition of this problem. Like assume that this is blue, then you have this circle, right, is blue but it has a red center. So basically, the idea is that you realize that these intersection points must be colored differently. Otherwise, you violate the condition of the problem. Remember, we're doing this proof by contradiction technique, but we need a contradiction that must be unavoidable. This contradiction can be avoidable because we simply just these are just different colors, right? By construction, they must be different colors. Um, so if they're not, then we have a contradiction. But we have to assume the case. Like for example, just think of it as this: we have two cases. Those points are colored the same, and if they're colored the same, then we have a contradiction, right? Because either this circle gives us a contradiction because if these are all blue, then this is also supposed to be blue, but it's not. And same thing for the other thing. If they're colored with red, that's one case. But in the other case, if they're colored different, we have to consider that, right? So that's basically just an argument. We just assume that we have this case, right? Like the other case is trivial because we have a contradiction. And actually, in the test, I didn't really even mention that. I just made an argument of like why these intersection points have to be colored differently. So these intersection points have to be colored differently. Um, but we are sort of, if you think about it, we are kind of getting closer, right? Because what we want in this problem is an unavoidable contradiction, an unavoidable situation where we have to have some sort of red or blue circle with a different colored center, right? That's exactly what we want. So in this case, we were kind of close because we got like two uh we got like two red points, but if we had like another red point, um we would have the contradiction we wanted. So, but there's a good thing though. Like drawing two circles gives you the intuition is that intersection points with different colored centers sort of creates like the beauty of these intersection points is that they force, right? They force a circle to have undesired points, right? Like for example, if I'm this if I'm the circle that has a blue center, I really don't want red points on my circumference because that's gonna like create a contradiction. But we do like as like the the mathematician in this problem, we do want that because that's a contradiction we want to find. But the idea is that these intersection points sort of gives these circles like undesired points. Like we know that because these points have to have different colors, then this blue centered circle is gonna have to have a red point, and it has no choice. And so That's the idea. Is we want to somehow because these intersection points, if they're the same color, we have the contradiction. So we realize is we kind of want to just abuse this fact, um, and that's exactly what we'll do. Is we'll abuse this fact. So what other color? What other? So now the question is, okay, what other circle should we draw? And we want to draw a circle that just creates more intersection points, and somehow these intersection points are going to, you know, lead us closer to a contradiction that we want. And so I was just thinking about it. Well, let's just like what points do we have? We've already drawn the circle at point P. We've already drawn a circle at point Q. Let's just draw maybe a circle centered at B, right? Right? These are concrete points that we can draw circles with. So if we draw a point centered at B, what should be the radius? Well, maybe the radius is just AB. So we'll draw like something, we have a radius, AB, and this is the circle we draw, centered at AB. So this is like what would happen, right? So now we think about it. Okay, so we need to keep track of everything we have in this problem. This is kind of getting a little bit weird, but if you think about it, so we drew another circle. This has a blue center, right? And so this should be a blue circle, right? But we have two new intersection points. So we have a blue circle because it has a blue center here. We have two new intersection points that we want to think about. This intersection point, this intersection point. The question is, let's just call these points. We're gonna call these points. I call them E and call this point F. So the question is, what should these be colored? Well, we're gonna think about the same idea. Like, let's just pick a color and see what happens, right? So let's say we both color. Let's say this is red. Like, think about it. You can't even color this red because if I color this red, right? Look at this circle here. So if I color that red, then this circle here, like that circle, is gonna have a blue center. We have a red circle that has a blue center, so you can't color that red. So you have to color it blue, right? And in the test, I actually marked. So the idea is that you realize that this red circle here, or technically it's supposed to be a blue circle because it has a blue center, right? It's supposed to be a blue circle, but you realize like because it has points P and A, right? If you have like it cannot take on any other red point on it, otherwise you'll violate the constraint. So because you know that this circle centered at Q cannot take on any more red points, it has to be colored blue. So first, maybe you like if you were to write this problem up, maybe you could just say like that the circle, like what I said is like that the circle cannot contain a red point. So you know that E must be colored blue. So the beauty of this circle is that somehow like you create an intersection point and you can use the advantage, you can use the idea that this must be blue. So this point over here has to be blue, has to be colored blue. Oops, should be. So this has to be colored blue. Okay, that has to be colored blue. Now look at this. The symmetry is a beautiful thing. So this is a red point, right? And so this is supposed to be a red circle, right? But you know that on this red circle you have two blue points. If F is colored blue, then you have a contradiction. So this must be colored red, right? Because if it's colored blue, you have contradiction because QBF will lead to contradiction. So you have to color this blue. Right? You have to color this blue. Sorry, you have to color this red. So like the question is, after three circles, we might stop and say, do we have any like so do you have any circle that so we know that like we didn't violate the condition for you know this circle, right? For this blue circle, for this red circle, and we didn't violate the condition for this blue circle, right? But did we violate the condition for the circle that we just drew, which is like this one? This is a blue circle that we just drew. Did we violate that condition? Well, we have two red point. It's supposed to be a blue circle, but we have two red points on it. And so if we have two red points on it, we didn't violate the condition. Um, if we had three red points, we would violate the condition. But we have like all of our circles are in danger zone, right? All of our circles are in danger zone. We have three circles and all of them are in danger zone. Like if we have one more point, for example, if this is in danger zone because this is a blue circle and we have two red points on the circumference, right? And and this is like a red circle. We have two blue points on the circumference over here for like this circle over here. And so basically, I call a circle like in danger zone if a circle is in danger zone if like it has it has 2 points on the circumference opposite of its center, right? That's in danger zone. We have three circles in danger zone, and so you know remember if we draw like intersection points be like if we draw a circle that intersects these like dangerous circles, then you know there might like we for example you might want to draw a circle that intersects like this circle here, right? And this circle here, because both of these circles are dangerous circles and like they both require that like you don't like for example in this circle its requirement is that you can't have another blue point, right? I should be using whatever, but and in this circle its requirement is that you can't have another red point or you're cooked. And so the idea is that these have different like requirements, opposite requirements. Maybe if you draw a circle that like intersects these two circles but create some intersection points but like that force them to only they to force them to be like if you create a circle that like intersects both of these circles, then you can't satisfy both of the conditions at the same time. Like the point has to be either red or green. I mean, or blue or red. And so like that like it's somehow going to like it's going to be impossible to satisfy both of them. So like what I'm saying is that like you should just have some intuition that like you should just draw like another circle. Um, and it's sort of hard to foresee this, but you have to play around with it. And so the idea here is that hey, we should try to draw maybe another circle. Where should we draw it? Well, let's just do like we draw a circle centered at B. Let's just draw a circle centered at A by symmetry, right? So we'll draw just another circle here. Centered, whoops. Center here. Now we have a bunch of madness, but we know that, okay, so now we look at the intersection points that we create. We create like a lot of intersection points. So we have this intersection point here, this intersection point here. I mean, the intuition is that intersection points are just like really nice. Um, intersection point here, intersection point here. Do we have another intersection point? Doesn't seem like we do. Yeah. So the idea here is that this is a red. So remember, circle centered at P is a red circle in danger, and so this has to be red. This point has to be red because if it's blue, it's a contradiction. And then we have intersection. Remember, this intersection point is on circle B, centered at B, but this is in danger, and so like it has two red points, so this has to be blue. So this point has to be blue. We're just using the same idea. So this point over here has to be blue. And then intersection point with this circle here, like this point is in danger and this point has to be blue here because it's on the circle centered at Q. So it has to be blue and it's in danger, so it can't be red. And then you look at this case, it's on this circle B, which has 2 red points, and so it has to be blue. But then you have contradiction because if this has to be blue, you realize like the circle centered at A with the radius AB, right? With the radius AB, it has 3 blue points, but it has a red center. So we have contradiction. And boom, that's it. It's literally it. Honestly, this was my solution on the test. Obviously, you would have to write it up a little bit more formally, but you didn't even have to be explicit with the coordinates. You just had to just draw a bunch of circles. But yeah. Honestly, this problem is like it doesn't require crazy intuition. Like it just requires you to understand that like first you have to start with 2 different like points, the different colors, but then just realizing that like drawing circles that are nice, and then like intersecting them with the other circles are nice. You don't really have to foresee exactly how things will come out, but the motivation is that like when you just draw circles that intersect with other circles that have like different like conditions, or like if you draw a circle that intersects another circle, it kind of forces points to be this color, but then it puts another circle in danger, and you sort of can just use the same sort of fact. That's basically all you had to do to realize to solve this problem, and it was pretty much that. Pretty much it. I'm sure there's like easier constructions, but I feel like my reasoning for where to draw the circles were like not even. It wasn't even that intelligent. I was just like, okay, I want to draw another circle. Where should I draw it? Let me just draw it at um like which points do I have? Okay, my circle's gonna be centered here. It's gonna have this radius. So that's pretty much it. But yeah, anyways, that's the Putnam B1.